In physics, you're often asked to think about systems of objects that are moving and interacting with forces in some way. For instance, let's say there's a kid moving in a shopping cart and they're both moving together at 2 meters per second on a frictionless ground. And then at some point, the kid is pushing forward on the cart, so it speeds the cart up, and then the cart, because of Newton's third law, we know pushes backwards on the kid, and let's say it makes them move in the opposite direction. So oftentimes, in a problem like this, you're thinking through momentum conservation. There's no outside forces, net forces on the system as a whole, the kid-cart system, and so the total momentum is conserved. And so if you know the mass of the kid in the cart, and the initial velocity, and you know the final velocity of the kid, you could predict the final velocity of the cart. But sometimes you're asked a question like this, where they give you the final velocities and the initial velocity of both. And the question is, hey, what's true of the speed of the center of mass of the system? Well, what is the center of mass of a system of objects, of the kid-cart system? Because, here, before the kid pushes off the cart, they're both moving at 2 meters per second. So whatever the center of mass is, it's probably moving at the same speed as both of them because they're both moving at that same speed. But afterwards, the kid is moving in the negative direction, the cart is moving in the positive direction at different speeds, and they maybe have different masses. What does it even mean to say that the system itself, or the center of mass of the system, has a velocity? And is it equal to 8 meters per second? Is it somewhere between the initial velocity and the final velocity of the cart? Is it less than the initial velocity of the system as a whole before? Or is it equal to the same speed the system was moving at before this force interaction event? So this whole video is going to talk through what is the center of mass? How do we know where it is for an object or a system of objects? And can the center of mass of a system move? Can it speed up? Can it slow down? All those questions will be answered. And once we understand what's true of the center of mass of a system of objects, we can even answer questions like this, where there's two carts coasting to the right in the positive x direction, and there's a string that's between these two things pulling them together, so it's slowing down the blue cart that's moving to the right, and it's speeding up the left cart that's also moving to the right. And the question is, based on this velocity versus time graph of each, does at least one of the carts experience a significant frictional force, one or both? The answer to that question has to do with thinking through the center of mass of the system. So let's get started. The system center of mass, as long as you have one object and if the mass of the system is uniformly distributed in this aluminum track, then the center of mass is where it sounds like it's in the center. It's exactly in the middle. And I've got a little purple dot here, which is placed in the very middle of the track. Now, one thing that's also true is if you take something's center of mass and you place it over some base of support, if the system center of mass is positioned over a base of support, the system will stay balanced and not rotate about the base of support. So you can see that when the dot is sitting on the base of support, it's balanced. This track doesn't rotate. But if it's not sitting over that base of support to the left or to the right, it's going to rotate either to the right or to the left. It's a little bit more difficult to think about where a system's center of mass is if we have multiple objects that are included in the system. So here we have a system that includes a track and the cart, and we know the track center of mass is in the middle, but where is the system's center of mass that includes the cart and the track? Well, we don't have a dot to see that, and actually where the center of mass is changes based on where that cart is. If the cart is to the right, you can see the whole system rotates to the right. That's evidence that the system center of mass was to the right of the book, the base of support. When the cart was moving to the left, the whole system rotated to the left. That was evidence that the system center of mass, wherever it was, must have been to the left of the book or the base of support. And so when we're dealing with systems of masses like this, where we have multiple objects that are moving, it's helpful to set it up at a base of support so it's balanced. And wherever it rotates, that'll tell us where the center of mass is, or at least whether it's to the right of the book, over the book, or to the left of the book. Now let's think through where the center of mass is for a little bit more complicated system. Our system is now going to be two carts and the track. Well, we know the track center of mass is in the middle, and if we had two carts of equal mass, where would the center of mass of just those two cars be? Well, if they have the same mass, their center of mass will be exactly in the middle of them, which you can see is over the base of support, along with the center of mass of the track. So if these things are at rest and everything stays balanced, that tells us that the center of mass of the two-cart track system is right in the middle. It's right over, somewhere over the base of support on that book. So let's see what happens if I push down on a little release trigger and make these things push on each other. There's a compressed spring inside of the red cart. It's going to push the blue cart to the right. And if the blue cart is getting pushed to the right, it's going to push back on the red cart to the left with the same size force, says Newton's third law. So let's just see what happens and talk about what the implications are. Okay, so you can see in the explosion from before, during the fact of the explosion, and after the fact, the whole track stays balanced. Let's see that in slow motion. You can see that the whole time from before the explosion to after the explosion, after they push on each other away, the whole track stays balanced. And what does that mean? If the whole track stayed balanced, that means the center of mass of the system as a whole must have stayed over the base of support, which was that textbook. So when they started at rest, they weren't moving, the center of mass was there. And as they moved away from one another, we know that in our explosions lab, we found out that when two cars have the same mass and they push on each other, after they push on each other, they're going to be moving off at the same speed. So the blue car is going to move the same distance away from that center line as the red car will, no matter what the time is. And so if they've traveled the same distance away from the center line at the same time, that means the middle of those cars will still be essentially where it was, which is over the base of support. And so the center of mass of the system as a whole, it started at rest and it stayed at rest. It didn't move from over that base of support. Another way to think about why that might be the case is thinking through what's true of the sum of the forces on the system. Well, on the two carts, like gravity pulls down, the normal force pushes up, and those external forces cancel each other out on these two carts. Same thing would be true of the track. Gravity pulls down on the track, the book normal force pushes up. So all those external forces cancel each other out. During the explosion or the pushing off event, those are internal forces. The force the blue car feels to the right, the force the left car feels to the left. Those internal forces don't matter. So the sum of the forces on the system is zero. And if the sum of the forces on the system is zero, the center of mass of the system will remain at rest. Because it was at rest, it's going to stay at rest. Well, what if we think through a situation now, same kind of thing, except they're not going to be equal mass ratios. The red car now has some added mass, so it's 4 times more massive than the blue car. And to start at rest, we had to kind of shift things over a little bit because there's more mass in the red than the blue. So the center of mass of these two cars is going to be a little bit, farther to the left. But I've set things up so that everything's balanced. So we now know that the track two-car system, where is its center of mass? Well, wherever it is, it has to be somewhere over that base of support. So let's find out now again, when we explode these things, when they push on each other and they go flying apart, where is the center of mass? Well, if I'm just pushing down, and this is a frictionless track, again, the sum of the forces still should be zero on the system the whole time. So as these guys move apart, the center of mass of the whole system should remain at rest, which means the whole track should balance. Let's find out if that's what happens. Let's see that in slow motion. We can see the whole time both cars are moving away from each other, the track stayed balanced. And what does that tell us? That tells us that the center of mass of the two-cart track system stayed at rest. It was still over the base of the support the whole time. In this case, even if the masses were different, the sum of the forces in the system was still zero. So if the center of mass was at rest, it's going to stay at rest because all the forces in the system cancel out. So in the case where the sum of the forces on the system was zero, let's look at what the velocity versus time graph looks like for both of these scenarios. The first one, the masses were the same. They both started with zero velocity, and if the blue car gained a positive velocity to the right, the red car would have had the same velocity back to the left because momentum should be conserved. There's no outside net forces. But what I want you guys to see is that the velocity of the center of mass of the system was zero, and we know it stayed zero because the whole track stayed balanced. And so when you look at this, as long as the masses are the same size, if two things push on each other, if we have the velocity of each of the parts of the system, what's true of the velocity of the center of mass of the system? You can see that it's exactly in the middle of the two individual velocities, and that's gonna be relevant later on. When we look at the velocity graph of the second situation, we know that each car started with 0 velocity, and the blue car gained a large positive velocity, and the red car gained a smaller negative velocity. If the mass of the red car was 4 times bigger than the mass of the blue car, we know that based on momentum conservation and our explosions lab, the blue car with 4 times less mass would have had 4 times a greater velocity. But even still, the velocity of the center of mass of the system was 0 and stayed 0 because the sum of the forces on the system was 0. And you can see that, well, what's true of the center of mass velocity of this system? It's not exactly in the middle of the 2 individual velocities like it was over here because the masses were not the same. The good news is in AP Physics 1, we're pretty much only going to see situations where objects are pushing on each other or moving away from each other or towards each other with identical masses. So if we have the individual velocities, we know that the velocity of the center of mass will be exactly in the middle of the 2 individual velocities. Okay, well, what if the center of mass of a system of objects is actually moving? The center of mass didn't start from rest, and so if the center of the mass is moving, like these 2 cars, they're moving together at some constant velocity on a level track with negligible friction. And the question is, well, what happens to the center of mass velocity? Well, if the sum of the forces on a system of objects is 0, the system's center of mass must either be at rest or move at a constant velocity, just like an individual object. If the sum of the forces is 0, if something's not moving, it stays not moving. If it is moving, it should move at a constant velocity. So how do we figure out if the location of the center of mass of these 2 cars continues to move at a constant velocity? Well, I put this into Logger Pro and graphed the position of the blue car over time, the position of the red car over time, and then was able to calculate the velocity of each. So from our position versus time graph, we can see that it's moving to the right at some slope, some velocity, and then after this is the explosion or where they're pushing off of each other, and afterwards it's moving to the right even faster. The red car is moving at the same initial velocity, and then it's moving backwards at some speed. So here's the velocity versus time graph. Well, where would the center of mass of the system be at any given time we check on this position versus time graph? It's got to be exactly in the middle of those 2 cars because these 2 cars have the same mass. And so the center of mass position will be exactly in the middle of the blue and the red dots on this position versus time graph. And so I calculated that. I'm just going to show you what that looks like. So these purple squares is the position of the center of mass of the 2-cart system graphed over time. And what do you notice? It's the center of mass is moving, its location is moving at a constant velocity, and then after the force interaction, after our little explosion, it stays moving forward pretty much at the same slope. When we look at the velocity versus time graph, the purple represents its velocity. It looks like the center mass was moving about 0.4, a little bit between 0.4 and 0.5 meters per second. And then after the explosion, it's still moving about 0.4, 0.5 meters per second. So the velocity of the system's center of mass stayed constant. And why would we expect that? Well, in this case, the sum of the forces on the system was 0 during this whole time, so we wouldn't expect the center of mass velocity to change, even though the velocities of the individual cars change. Now, let's just take a look at our velocity versus time graph one more time and notice, like, where is the center of mass velocity of the system compared to the individual velocities? Well, you can see it's like right in between. It's right in the middle of the blue car's velocity and the red car's velocity when they're moving in different directions at different speeds. So, to summarize, if the sum of the forces on a system of objects is 0, the system's center of mass velocity will not change. If it's moving, it will continue to move at the same speed in the same direction. Well, what happens to the center of mass, or the velocity of the center of the mass, if the sum of the forces on the system as a whole is not 0? We've seen 3 situations, 2 where the center of mass was at rest, and it stayed at rest, explosions on that balanced track. And we just saw a situation where the center of mass was moving, and it stayed moving at the same speed in the same direction because the sum of the forces also, again, was still 0. But if we have an explosion on an incline like this, the sum of the forces is not 0 because there's gravity pulling down on the system, the normal force is pushing up perpendicular to the track, and there's some component of gravity left over in the x direction, parallel with the track, that's speeding up the system before the explosion. So the center of mass of the system will actually be increasing speed. And the question is, after the explosion, does it continue to increase speed? What happens to the center of mass position and or velocity during this whole event? So again, I did some video analysis. I marked the position of the blue car before the explosion and after the explosion, and again, the position of the red car. And I also then graphed the velocities. So if we want to figure out what's true of where the center of mass is of the two-car system, again, it's going to be, since these are the same mass cars, it's going to be exactly in the middle of these two position values at any time we check. And so again, here's a curve, a purple curve, which shows the middle position between the blue car and the red car for every time. And you can see that the center of mass position is, it's got kind of a top opening parabolic relationship. It's getting steeper and steeper and steeper. So the center of mass is speeding up. Well, when we look at our velocity versus time graph, it's a little bit clearer. So we see the blue car and the red car are speeding up at a certain rate. They have a certain acceleration together based on the sum of the forces being the x component of gravity. That's what's speeding them up. And then the explosion, the blue car gains an even larger positive velocity, then continues to increase in speed. And the red car, the force that it feels actually slows it down and makes it move in the opposite direction, gives it a negative velocity. And then as it goes up the incline, the x component on it is decreasing its speed. It's making its velocity go back to zero. But what do we notice about the velocity of the center of mass of the system? Well, that's in purple here. We can see that the center of mass is increasing in velocity in a linear way before the explosion, and after the explosion, and during, it still increases in a linear way. So what can we conclude from this? We can conclude that if the sum of the forces on a system of objects is non-zero, so it has a certain value, like in this case, the system's center of mass velocity will change. In this case, the system's center of mass velocity increases at a constant rate because it feels a constant component of gravitational force parallel to the ramp, right? It was increasing in speed in the same way because the sum of the forces on the system as a whole didn't change in size. The amount of gravity parallel to the ramp was constant. So therefore, the acceleration of the system must also be constant. Even if parts of the system are doing different things, the system as a whole, the center of mass location, will keep doing what it was doing as if this explosion actually didn't happen. So in conclusion, how do we know how a system's center of mass moves? It has everything to do with the sum of the forces on the system. If the sum of the forces on the system is zero, that means if it starts at rest, it's going to stay at rest. If it's moving at a certain velocity, 0.4 meters per second, it's going to stay moving at 0.4 meters per second. And if the sum of the forces is non-zero, like in this case, the x component of gravity, that means that the center of mass is going to be changing velocity. And because the system was moving to the right initially, and the sum of the forces is in the same direction, that means the speed is going to be increasing. The velocity in this case is getting more positive over time. So now that we know that about a system center of mass, let's go back to those two initial problems and kind of think these through. How do we use this knowledge to solve a physics problem? So question number one was, which of the following is true of the speed VC of the center of mass of the kid cart system after the kid pushes off the shopping cart? So we've got the initial velocity of the cart and the kid. It's 2 meters per second. So that's got to be the velocity of the center of mass of the system. They're moving at the same speed, so the center of mass will have the same speed. And afterwards, even though the kid is moving to the left backwards, the cart moves to the right at a faster speed. Again, we have to ask the question, what's true of the sum of the forces? Right? Well, go back to the situation we looked at with the two carts moving on the track. We said the sum of the forces on the system as a whole, as long as there's negligible friction, that these two pushes are internal to the system. The sum of the forces on the system is zero, and we know that when the sum of the forces on a system is zero, an object's center of mass velocity will stay constant. It will keep doing what it was doing. So if before this force interaction, the system was moving at 2 meters per second, that means the velocity of the center of mass of the system has to still be moving at 2 meters per second. And we saw evidence of that when we looked at the video analysis data of this moving explosion on a level track. We'll end this video with our last example problem where we're going to be able to use what we know about the center of mass of a system to answer this question. So the question reads, two identical carts are moving in the positive x direction. The carts are connected by a string attached to a small electric motor. The string is used to bring the carts to the same speed. The graph shows the speed of the two carts during a 4-second interval. And the question is, does at least one of the carts experience a significant frictional force and justify a response? So all we're given is this scenario and the velocity versus time graph. Well, if there's a significant frictional force on either one or both of the carts, that would be an external force on the system as a whole, right? And so the question, is there an external force on the system? And if so, there must be some significant frictional force on either one or both of the carts. So we have the velocity of two parts of a system. And the question is, well, what's true of the velocity of the center of mass of the system, which is going to help us answer our question? Well, we have to come back to the first clue right here. It says it's two identical carts, which means they have the same mass. And if there's two parts of a system that are pulling or pushing on each other, and we have the individual velocities, what's true of the velocity of the center of mass of the system, where the masses are the same? Remember, it's in between the velocities of each part of the system. So let's add some dots on this graph in between each of the given velocities at specific times. So at time 0, the red car is moving at 1 meter per second, the blue car is moving at 4, and right in the middle would be 2.5 meters per second. So at whenever the clock started, the velocity of the center of mass was moving at 2.5 meters per second. And for 1 second, it's going to be located about there. At 2 seconds in between, it's going to be right about there. At 3 seconds, it's here. And you can see at 4 seconds, they are moving at the same velocity. And so we can connect those lines and show that, hey, here's how the velocity of the center of mass of the two-cart system is changing. Well, and it is changing. It started at 2.5 meters per second, and it goes down to 2 meters per second, which means the system's center of mass is decreasing speed. The velocity is getting less positive over time, which means there must have been a net force on the system, an external force. And what's the only thing we can blame for that? That would be friction. So if the system's center of mass velocity is decreasing over time, the system must be experiencing an outside net force in the negative x direction, in the opposite direction the system is moving. Therefore, one or both of the carts must be experiencing a significant frictional force. And I just want to tack on one added little bonus question. You might be asked, okay, so there is an outside net force, this frictional force, and the question is the frictional force increasing in size, decreasing in size, or is it a constant frictional force over that 4-second interval of time as shown on the graph? Well, we've got to think about how the velocity is changing. The velocity is changing, the center of mass velocity is changing in a linear way. So, and the slope of a velocity versus time graph is the acceleration. So that means the system has a constant acceleration. And things only feel a constant size acceleration is if the sum of the forces is also constant. So we could say, according to the graph, the center of mass velocity is changing linearly. It has a constant acceleration, which is the slope of the velocity versus time graph. Since the center of mass acceleration is constant, it must be experiencing a constant net force. That tells us that the frictional force, if we were to graph it over time, will be the same value over those 4 seconds. I hope this video has been helpful in allowing you to determine what the center of mass is, where we can find it, and what happens to the center of mass location. Does it stay at rest? Does it move at a constant velocity? Or does it constantly change its velocity or decrease its speed or increase its speed? It has everything to do with the sum of the forces on the system.